Hello everyone, welcome to my YouTube channel. Krish here with another physics video. In this video, I'm going to discuss about Coulomb's law and its applications. Some sort of basic problem solving strategies. But before that, if you are new to my channel, please don't forget to subscribe, hit the bell icon in order to get the notifications. And if you need any assignment help, please mail me on ephysicsvideos@gmail.com. Now, let's quickly get into the topic. The topic is Coulomb's law. So, what is meant by this Coulomb's law? Coulomb is a scientist who has studied the electrostatic force between the charges. Okay, so according to his observations and experimental results, the electrostatic force between the two charges is identified as directly proportional to the product of the charges, and this force is inversely proportional to square of the separation between the charges. Let us consider two charges q1 and q2. Let's say these two are separated by a distance r. Now the electrostatic force between these two charged particles is directly proportional to the product of the charges, and this force is directly proportional to 1 by r square, inversely proportional to square of the separation between the two charges. Now if I combine these two relations, I'll get F proportional to q1 q2 by r square. Now in order to remove this proportionality, I have to introduce a constant, and that constant I am introducing it as k, q1 q2 by r square. So this k is the proportionality constant. T constant. Okay, now this k value, let's say these two charges placed in vacuum, then this k value will be equal to 9 into 10 to the 9. Again, this value is experimentally identified, so the values of k is 9 into 10 to the 9 when the two charges placed in the air medium or vacuum medium or free space. Okay, now again this k value, k experimental relation, the relation for k is given as 1 by 4 pi 1 by 4 pi epsilon naught. What is this epsilon naught? Epsilon naught is the permittivity of free space. That means air. Okay, so permittivity of free space, and its value is, we know this value, epsilon is equal to 8.85 into 10 to the minus 12 Coulomb square per Newton meter square according to the relation. Okay, so finally we have got the electrostatic force between the two charges as 1 by 4 pi epsilon naught q1 q2 by r square, right? And this epsilon naught is the permittivity of free space. So this is the expression for the electrostatic force between the two charges when they are placed in the air medium or vacuum medium. Now the question is, how the force changes if they are placed in any other medium. Okay, let's say these two charges placed in some other medium, then the electrostatic force becomes 1 by 4 pi epsilon q1 q2 by r square, right? Here epsilon is the permittivity of the medium in which the two charges placed. Permittivity of the medium in which the two charges are placed. Okay, now I'm going to give you a relation, that is relative permittivity, and this relative permittivity of the medium is defined as the permittivity of that medium to the permittivity of free space. Okay, this relative permittivity is also known as dielectric constant. Actually, this dielectric constant can also be represented as K, capital K. So in order to avoid the confusion between this, sorry, in order to avoid the confusion between K that we have used in electrostatic force expression and this K, I am using simply epsilon r for the dielectric constant here in this equation. Okay, now I can rewrite this equation as epsilon is equal to epsilon naught into epsilon. Now I am replacing this relation into here. Now what I am getting, so this f dash, let's say 1 by 4 pi epsilon naught, and epsilon r I am writing here. Okay, q1 q2 by r square, right? So what I'm getting exactly, f dash is equal to 1 by epsilon r into f. So this 1 by epsilon naught into q1 q2 by r square, this whole term can be represented as f itself, right? So that means when the two charges placed in the air medium. So I have got the relation f dash is equal to 1 by epsilon r into f. So this means what? As the dielectric constant value increases, the force between the two charges decreases, and vice versa, right? So the final expression for the electrostatic force is 1 by 4 pi epsilon naught into epsilon r q1 q2 by r square. So this is the ultimate expression for electrostatic force between the two charges when they are placed in some other medium of dielectric constant epsilon r. Okay, now from in this expression how many variables I'm getting? If you clearly identify, force is one variable, charge is one variable, I mean q1 and q2, let's say. Okay, and distance between the two charges is another variable, and I left with one more variable, that is epsilon r, because it varies with the medium. Sorry, so because it varies with medium, right? So I have got four variables here: force, charge, distance between the charges, and dielectric medium, I mean medium in which the charges are being placed. Now if I if I keep two of the variables as constants, then I can get the relation between the other two. So I'm taking the first case. Okay, in the first case what I'm going to do is I will consider the distance and dielectric constant as constants, medium as constants, right? In that case I'll get the relation between force and the charges. If one of the charge or both the charges increases, then the force between the charges also increases. Okay, and if charges decreases, then the force obviously decreases. Now coming to the second case. In this case what I'm gonna do is charges I'm keeping constant, and the electric medium also keeping constant. Then I can get the relation between force and the distance between the two charges. So from this relation we can conclude that as the distance between the two charges increases, then the force between the two charges decreases, and vice versa, right? So from this relation we can also conclude that this electrostatic force obeys inverse square law. Inverse square law. Okay, why, I mean why it obeys inverse square law? From the relation itself you can read it out like the force is inversely proportional to, that means inverse proportional to square of the distance. That means it obeys inverse square law, just like gravitational force. And the gravitational force is also, we have studied it, it varies with, I mean it is inversely proportional to square of the distance between the two objects. Similarly, okay, similarly electrostatic force also obeys inverse square law. Okay, just like gravitational force. Now coming to the next case, third case, right? Okay, third case, let's say. In the third case what I'm going to do is I'm keeping charges and the distance as constant. So I'm getting the relation between force and the dielectric constant. This relation that we have already discussed. As the dielectric constant increases, the force between the charges decreases. That means the force between the electric charges varies with the medium. Okay, so inversely proportional to dielectric constant. Now let us go to the next relation. Okay, now I'm considering the two charges here. Okay, q1, q2, let's say, and these two are separated by distance r, let's say. Okay, now the force on 2 due to 1, force on 2 due to 1, it acts towards left, right? There exists repulsion, right? There exists repulsion. So q1 charge pushes q2 charge towards right. Similarly, q2 charge pushes q1 charge towards left, I mean right. Q force on, sorry, one second. So this force is right. This force is right. And what about this force on 1 due to 2? That is to the left. Again, repulsion. So these two forces are acting in opposite directions, right? This is F21 and this is F12. So there exist opposite forces. Now coming to the next conclusion, that is the magnitude of two forces is same. Magnitude of two forces is same because K into Q1 Q2 by R square. Similarly, K into Q1 Q2 by R square. So magnitudes are same. So we have got the conclusion: the two forces are acting in opposite directions and their magnitudes are same. If you clearly recall a law which just explains these statements, I mean which just comparable to these statements, is nothing but Newton's third law. According to Newton's third law, there exist equal and opposite forces. Okay, and those two forces are acts on two different objects. In our case also, the force 2(1) is acting on q2, force 1(2) is acting on q1. So these two forces are acting in opposite directions and with same magnitudes and acting on two different particles. So we can simply conclude that electrostatic force obeys Newton's third law of motion. Okay, right. We have got the conclusion. Now we'll get another conclusion from this, observation. If I would say, I'll take the same illustration again. Q1, Q2 separated by distance R. Okay. Now what exactly happening is F21 is acting in this direction. Similarly, F12 is acting in this direction, right? So these two forces are acting in opposite direction along the line joining, right? Line join. If you reconsider this, instead of taking two positive charges, if I would have taken a negative charge, then exactly what happens? Let's say r distance. Now force on q2 due to q1 is attractive, and so it acts in this direction, F21, and force on 1 due to q2 again towards right because of attraction, F12. So these two forces are also acting in opposite directions and along this line joining the two charges only. So what we have clearly observed is the electrostatic forces are acting either away from the center or towards the center along the line joining the two charges, right? That is why this electrostatic force is regarded as as a central force. Central force. Okay, so this is a central force. Now coming to the next point. Why we have called it as a central force? Because it always acts towards the center or away from the center based on the nature of the charges. Okay, so this is one conclusion. Let us get another conclusion. Let us discuss another important property of the electrostatic force. Okay, now in case of gravitational field, what we have observed is, if there is a box on the surface, if I would have displaced this object to a height h in along this path, and in the second case what I did is I have displaced this object along this path to a same height again. Okay, what is the gravitational potential energy stored in both the cases? This is mgh, and in this case also mgh, that means work done by the gravitational force is same in both the cases, and it is independent of the path followed. Just like this case, similarly electrostatic force is also, similarly work done by electrostatic force is also independent of the path followed. So this electrostatic force can be considered as a conservative force, just like gravitational force. So electrostatic forces on two different objects acts in two opposite directions, either irrespective of nature of the charges. If both the charges positive, acts away. If both the charges negative, acts away. One of the charge is negative, one charge is positive, then acts towards. So however, the two forces acts in opposite direction with of equal magnitude, acts along the line joining between the two charges, and acts towards or away from the center. So it is a central force, and the work done by the electrostatic force is independent of the path followed. So this electrostatic force is regarded as the conservative force. Okay, now let us discuss one more property. Okay, now I would say, let us take two charges here, q1, q2. Okay, and separated by distance r. Now the force on q1 due to q2 is k q1 q2 by r square. I am writing this k directly, in spite of writing 1 by 4 pi epsilon naught. So in order to have a simple equation. Okay, so that is why I am writing k instead of 1 by 4 pi epsilon naught for simple equation representation. Okay, now what I'm going to do is, I have taken another charge, let's say q3 minus. Okay, I have placed it in the vicinity of these two charges, let's say. Now the force on this minus q3 also exerts some force, right? It attracts, and this q2 repels this q1. Now on placing this charge minus q3, the force on q1 due to q2, a third charge, in the vicinity of the other two charges the force between Q1 Q2 will not be affected, affected affected. Okay, so the force F12 will not be affected on placing the third charge Q3. So this is one most important point that that is related to electrostatic force. These are the basic and important properties of electrostatic force. Now let us discuss some of the problem solving strategies. Okay, so in this video I am discussing the Coulomb's law and some basic properties of the electrostatic force. In addition to that, some basic problem solving strategies which involves electrostatic force. Okay, and I have divided uh, this concept Coulomb's law, electrostatic force and applications in 3 sessions. Okay, in this video I'm discussing the Coulomb's law and the properties and some basic problem solving strategies. In the next video I'm gonna discuss about some high-end problem solving strategies, like we are going to apply this electrostatic force to SHM. We are going to apply this electrostatic force to equilibrium problems. We are going to use this electrostatic force in circular motion as well. Okay, and in the third video I'm going to explain the vector form of Coulomb's law. In addition to that, some problem solving strategies of vector form of Coulomb's law. Okay, so please be sure to subscribe and hit the bell icon in order to get the notifications as soon as I upload the videos. Okay, and if you need any assignment help, please mail me on ephysicsvideos@gmail.com. Okay, let's get back to the discussion. Now let us take the first example. Simple. We'll start from simple to complicated ones. Let's say I have given an example like a question like there are two charges, 1 coulomb and 2 coulomb, separated by a distance r. R is equal to 1 meter. Let's say, for simplicity I'm taking simple numbers. Okay, 1 meter. Now what is the force between the two charges? You can simply ask it something like that. Okay, and what if the what is the force if the two charges placed in some other medium of dielectric constant 20, dielectric constant 20. Okay, so there are two questions you have been asked to find. So we'll start with the first one. So we know the relation F is equal to K Q1 Q2 by R square, right? So this K value is 9 into 10 to the 9. Q1 is 1 coulomb and 2 coulombs and 1 meter square. So you can simply calculate it. That is 18 into 10 to the 9. It is a very large value because we have taken a large value of charge. Okay, 1 coulomb. Coulomb is a very large value. Coulomb is a very large value as per our discussion, number of electrons. Q is equal to Na, that we have already discussed in the earlier session. From this relation, N is equal to Q by E. So Q is equal to 1 coulomb, 1.6 into 10 to the 19 minus. So if you calculate this value, 6.625 into 10 to the 18 electrons you will get. So these many number of electrons are required to get 1 coulomb of charge. That means 1 coulomb of charge is a huge value. That is why we often use the charge values as microcoulombs, microcoulombs or nanocoulombs or picocoulomb. In very rare cases like millicoulombs we use. Okay, but however 1 coulomb is a very large value. That is the reason we have got this much force between the charges. Now coming to the next case, so this f dash. Okay, now this k into q1 q2 by r square by epsilon r, right? This k is what? 1 by 4 pi epsilon naught. So we will get the same relation, right? So that in that case, what is happening? 9 into 10 to the 9 by k value is 20, and q1 is 1 coulomb, q2 is 2 coulombs, and the distance between them is 1 meter square. So if you simplify, what you will get? 2 tens, 10 will get cancelled, 9 into 10 to the 8 newtons. So this is also a large value because we have considered the same amount of charges, right? So this is how you can approach to solve a problem when it is given with multiple, two charges, in order to find and ask to find the electrostatic force between the two charges. Okay, hope this example is helpful to you and very easy to understand because it is a simple one. Okay, now let's get to the other illustration, other example. Okay, but before this example discussion, let us understand some other important point. Let us say I have taken q1 and q2 just like earlier, separated by a distance r. Okay, now these two charges are being isolated. Okay, what is this? Isolated, that means no external force is acting on the system. Sorry, isolated. Example, isolated. Okay, this is here, isolated. Okay, if this is isolated, the net external force acting on the system is 0. Now if you clearly see, F21 is acting in this direction and F12 is acting in this direction, right? What is the net force inside the system is 0. F net is 0, F external is also 0, F external is also 0, right? So what is the net force? Is 0 again. So whenever it comes to a discussion of net force 0, we can have the relation dp by dt is equal to 0. So we get p constant, right? What is meant by p constant? P constant means p will be conserved here. P will be conserved, right? P will be conserved. So if P is conserved, we can apply this conservation of momentum to the given illustration, right? So in order to make you understand this, concept, let me take an example. Okay, so I have taken 1 coulomb of charge and 2 coulombs of charge. Okay, and the particles having masses 1 kg and 2 kg respectively, separated by a distance r. Let's say r is equal to 1 meter, let's say, for simplicity. And these two charges are fixed initially. Fixed. Now once the charge is left free, if charges left free, then what happens? They fly away. They fly away because of the repulsion, right? After some time, this 1 kg particle is observed to be somewhere here, and which is moving with a speed of 2 meter per second, let's say. Now you have been asked to find the exactly at that instant what is the speed of this particle. You have been asked like that. You can simply apply the conservation of momentum like 1 kg into 2 meter per second, or you can go in details like P initial is equal to P final. That implies P initial, the total system, initial system is 0 because there is no motion, and final m1 v1 plus m2 v2. Now if you clearly write the equation, v2 is equal to minus m1 by m2 into v1, right? So m1 is 1 kg, m2 is 2 kg, v1 minus, I'm writing here v1 is the leftward direction, so 2 minus 2. So what I'm getting? I'm getting 1 meter per second. I have got positive value, so it must be moving towards right. So this is how you can approach to a problem whenever it is asked to use conservation of momentum while you're considering the electrostatic force. Okay, now separated by 1 meter distance, 1 kg mass, 2 kg mass, separated by distance 1 meter distance. So and now what exactly happening is, this is again isolated system. Okay, now what we need to find is, let's say initially these two are fixed. Now after some time I left them free. Okay, then what happens? They actually fly away. So once they fly away along the line joining only. So then what happens exactly is, this q1 can be observed somewhere here. So this is x1, let's say, and this q2 must be observed somewhere here, x2 distance. Let's say x1 is observed to be 2 meters. Now you are asked to find x2. You can simply calculate it as, you might have remembered, when the net force acting on the system is 0, then the displacement in the center of mass should be 0. That means 0 is equal to x1 m1 x1 plus m2 x2, right? The moment of center of mass or moment of mass is constant because the center of mass is not moving when the net external force is 0. So this is how you can represent the equation, and you can find the x2 by just rearranging this equation, m1 by m2 into x1 minus r. So we have the values 1 kg, 2 kg minus x1 is in leftward direction, so I'm writing minus 2 meters. So what I'm getting is 1 meter. Positive sign indicates it is moving towards the right. So this is another kind of example where you can get these kind of examples in competitive exams. Okay, now let us go to next example. So in this example I'm going to consider 3 charges. I'm going to place them on the vertices of equilateral triangle. So 1 coulomb, let's say, 2 coulombs, let's say, and this is minus 1 coulomb, let's say. Okay, now the question is asked to find the net force on 1 coulomb charge. F force on 1 coulomb charge is equal to how much? Okay, right. Now there will be a repulsion here and there will be attraction here, right? So the force due to 2c on c is in this direction, that is F1, let's say. Now force on this 1c due to minus 1c coulomb is attractive, so this minus 1c pulls this force, pulls this 1 coulomb charge because of the attraction. So let's say this is F2. Okay, now I'm gonna find F1 first. Okay, I'm keeping it as it is for making this calculation simple. Okay, Q1 is how much? So this is 1 coulomb and minus 1 coulomb. I'm writing the magnitude only. So I'm considering this minus sign. Okay, so this is 1 coulomb again, magnitude for magnitude. So as I have already told you, this is an equilateral triangle, so sides must be equal, which is equal to 1 meter square. 1 meter square here I'm writing. Now what I'm getting, K I'm getting here. So F2 direction I have already represented. F2 is equal to K, F1, let's say. Okay, so F1 I have written it as wrong. Let's say you can consider you know this can be as f2 and this can be as f1, let's say. Okay, I've written f1 and f2 I'm writing. So 1 coulomb and 2 coulombs by 1 meter square again. So what I'm getting 2k. Now what I'm gonna do is I'm gonna resolve these two vectors into x and y components for simplicity. Okay, so let us express the x component of f2, f1, let's say. So as it is an equilateral triangle, angles must be equal to 60 degrees, right? So what is the component along x direction? f1x is equal to f1 cos 60, right? So f1 is, you know, k cos 60. Cos 60 value is 1 by 2, so k by 2 I'm writing it as f1x. Now f2x is minus f2, that is equal to minus 2k, because this component is along negative x direction, right? Okay, now let us discuss the vertical components. Okay, so in case of vertical component, you have f1y. f1y is f1 sine 60. So root 3 f1 is k, right? K by 2, right? And f2y is equal to 0 because it is acting along the negative x direction. It has no projection on y axis, so f2y is 0. So fx net is equal to what? K by 2 minus 2k. K by, sorry, k by 2 minus 2k, right? Similarly, fy is equal to how much? f1, that is root 3k by 2. Now we have got the, you know, this fx and fy. You can simply calculate the f magnitude under root fx square, sorry, fx square plus fy square. Okay, by substituting the expressions, fx and fy here, you will get the magnitude simply. And in order to get the direction of this resultant, tan inverse of fy by fx, you can find the direction by substituting the quantities here. Okay, here I have used the k as it is, but instead you need to substitute the value of k, that is 9 into 10 to the power 9, in order to get the final answer as a numerical value. Okay, so these are all the equation that has to be taken care in order to get the correct final answer. Okay, so this is one kind of example. Let us go to another illustration. Now let us take instead of 3, this time I'm taking 4 charges, let's say. Okay, so these are the 4 charges. Let's say 1 coulomb is here, 2 coulombs is here, and here also 1 coulomb, here also 2 coulombs. Okay, now what is the force on charge q? What is the force on charge q placed at the center? Placed at the center, and this is a square of side length 1 meter each. Okay, now by symmetry you can say net force is 0. Let me tell you how. So this is the point charge q, let's say. Okay, now this is 1 coulomb charge. This 1 coulomb charge pushes this charge in this direction. Similarly, this 1 coulomb charge also pushes this charge in this direction, right? So the net is 0. Okay, f along this so they cancel out, right? Similarly, if you consider the next set of charges, so this is Q, let's say, and this is 2C. What happens? This 2C will pushes this charge in this direction. This 2C pushes this charge in this direction. Similarly, this 2C pushes this charge in this direction. Here also the forces cancel out. So F net must be equal to 0. Okay, so by symmetry also we can say the net force acting on the particle which is at the center of the given square is 0. Okay, now let us discuss one more such example. Okay, I'm taking, so this is a square. Let's say here I have 1 coulomb, here I have 2 coulombs, and here I have minus 1 coulomb, here I have minus 2 coulombs, let's say. Then what is the force on the particle of charge Q, which is exactly at the center of the square of side 1 meter? Okay, so this is again the simple kind of problem you can approach in the similar way. So I'm taking, this is the charge Q, let's say. Now this is 1 coulomb charge. This 1 coulomb charge pushes this charge. Similarly, here minus 1 coulomb charge is there, right? This minus 1 coulomb charge also it pulls the Q charge because of the attraction. This repels, I mean, so it acts in this direction. This attracts. So these two forces add together to give the net force along in this direction. Okay, so F1, let's say F1 is equal to K 1C Q by, let's say this distance R at the initial, plus K magnitude 1C and Q by R square again. Now what is the result? That is 2KQ by R square. Similarly for the minus 2 charge also, F2. So F2 is acts in this direction, right? F2 is equal to K2C Q by R square, K2C Q by R square, right? What I'm getting? So I'm getting final equation says F2 is equal to 4KQ by R square. I'm just using the variables. We'll substitute the numerical values later. Okay, so F1 we have already got. F1 is equal to 2KQ by R square, right? So what is the angle between these two? If you clearly observe the angle between these two, this is acting in this direction, this force is acting in this direction, right? The angle between these two must be 90. So the resultant that we can simply calculate, F is equal to FQ, force on charge Q, under root F1 square plus F2 square. You can simply substitute them, right? So 16 KQ by R square plus 4 KQ by R square whole square, this also whole square under root. So what I'm getting? I'm exactly getting root 20 into KQ by R square. So this is what I have got. So K value that we already know, 9 into 10 to the 9, and R value we can calculate. I'm calculating the R value. Let us take the diagram here. So this is 1 meter and this is also 1 meter center, right? So this is 1 by 2 and this is also 1 by 2. So what is R value? R is equal to, we can calculate, r is equal to under root of 1 by 4 plus 1 by 4, that is 1 by 2 square, 1 by 2 square, right? So 2 by 4 is equal to 1 by 2 under root 1 by 2. You can write it 1 by root 2. So r value that we have got, r square is equal to 1 by 2. R square is equal to 1 by 2. Now substitute these two, this one and this one here. Now what I'm getting, F Q, force on Q, is equal to K is 9 into 10 to the 9 Q into root 20 by 1 by 2. So what I'm getting, root 20, 18 root 20 into 10 to the 9, okay, whole into Q. So this is the answer that I have got. You can further simplify this equation. Okay, so this is how you need to approach a problem which involves multiple number of charges. Hope the example provided is helpful to you, right? Now let us apply this electrostatic force to simple mathematics related problem. Okay, so I am taking an example here. Okay, so there are so many problems that involves electrostatic force and simple mathematics and vectors. Okay, but I am discussing some of them so that you can understand how to approach a problem which involves electrostatic force and vectors, electrostatic force and mathematics. Okay, right. So what I'm going to do is I'm taking an illustration, something like that. So here at the origin I have placed 1 coulomb of charge. Okay, now I have placed another 1 coulomb of charge at 1 meter distance, and I have placed 8 coulombs of charge at 2 meter distance, and I have placed 27 coulombs of charge at 3 meter distance, and so on. I have placed 1000 coulombs of charge at at a 10 meter distance, let's say. Now you have been asked to find the what is the force on 1 coulomb charge. Okay, net force on 1 coulomb charge due to all these 10 charges. Okay, I'm writing the expression F1C on this 1 coulomb exerts repulsive force. It also repulsive force. So all the forces are repulsive, and so they are acting in same direction. If the vectors acting in same direction, they can directly be added. Okay, so there is no complication here. Right, what I'm gonna do is I'm gonna take K as it is for simple calculations. Okay, K into 1C by 1 meter square. Similarly, K 1C and 8C by 2 square, and K 1C 27C by 3 square. Similarly for the last term, that is K 1C 1000C, okay, by 10 square, right? So if you simplify, I have written K everywhere, so I don't need to consider this. Okay, so I'm taking K as common here. Okay, now what I'm gonna write is first term is 1, as you can see, and the second term is, as you can see, this 8 coulombs can be written as 2 cube, right? And this 27 coulombs can be written as 3 cube, and this 1000 coulombs can be written as 10 cube, right? So what I'm gonna do is, this is 2 cube by 2 square and 3 cube by 3 square. Similarly so on, 10 cube by 10 square, right? So what I'm getting finally, I'm just getting a simple expression like 1 plus 2 plus 3 so on and 10 terms. Okay, so this is a mathematical approach. Here you need to approach mathematically, like this is a series. and you can identify what kind of series it is by recalling the details of HPGP and all. Okay, so by using that I can write K is equal to n into n plus 1 by 2, right? What is n here? Maximum value. So K into 10 into 10 plus 1 by 2. How much I'm getting? I'm getting 55K. So this is my answer. If you still want a numerical answer, you need to substitute the value of K. K is how much? 9 into 10 to the 9. Okay, if you substitute that value here, you will get the final answer. So 55K is the answer in our case. And there is still a kind of question, a little bit tricky question, let's say. Example I'm discussing. I have discussed so many examples to make you understand how to approach a problem when it involves electrostatic force. Okay, right. So I'm taking a clock here. Clock means there will be needles and there will be numbers. This is 12 coulombs and 1 coulomb, 2 coulomb, 3 coulomb, 4 coulomb, 5 coulombs, 6 coulombs, 7 coulombs, 8 coulombs, 9 coulombs, 10 coulombs, and 11 coulombs. Okay, so this is what I have considered so far. Now here I have placed a charge Q exactly at the center. Now I have asked to find the net charge on Q. Can we calculate it? Yes, of course we can calculate it. Let's say the force due to this 6 coulomb charge in this direction and the force due to 12 coulomb charge in this direction. So what will be the net charge here? So what will be the net charge? If let's say this is K, you know, 6 coulombs minus 12 coulombs, 6 coulombs into charge Q by distance. Let's say this is 1 meter. Okay, 1 meter. So 1 square. I have taken it directly. Okay, so you don't need to it is not a complicated thing. If you want me to do it completely, I'll do it. No worry, I'll do it. Okay, let's say so this is force 1. 1 second. This is force 1. F1 is equal to, this is in upward direction, this is downward direction. Let's say downward as positive, upward as negative. K Q 12C by 1 meter square. Similarly, upward force as a negative, K Q 6C by 1 square. So what I'm getting? I'm exactly getting K 6KQ is the value that I've got so far. So you need to follow the same steps for all kind of charges. So this is 7 and 1, 6 coulombs again. This is 2 and 8, 6 coulombs again. 3 and 9, 6 coulombs again. 4 and 10, 6 coulombs again. 5 and 11, 6 coulombs again. I mean, sorry, 6 coulombs again, right? So forces, how the forces differ. What is the resulting diagram would be? Let us say this is Q. Now this is the force. How much I have got? 6KQ, right? Now similarly, when it comes to this one, what I'm getting? So this one, 7, due to 7 there will be force. So this is 6KQ again, and 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 this is 6KQ. So this is at 1 Coulomb charge, at 2 Coulomb charge, at 3 Coulomb charge, at 4, at 5, at 6 Coulomb charge. So what have got similar amount of charges, right? So if you clearly observe, the vertical components of this one and this one, this one cancel out. So when it comes to net x component, I am rewriting. So what is the angle here? It is 60, it is 30. Okay, and similarly this is 60, this is 30 again. Okay, so this is 60, this is 30, and this is 60, this is 30 degrees, right? So vertical components cancel out. Fx is equal to, Fx is how much? So 6kq cos 60 plus 6kq cos 30. Okay, due to this one as well. Okay, 2 into, sorry, plus 6kq cos 60 plus 6kq cos 30. If you clearly recall, 30. Okay, if you clearly recall, cos 60 value 1 by 2, and there is two terms, 1 by 2 1 by 2 will get cancelled. 6 1 1 by 2 cos 60 2 1 by 2 and 6kq cos 60 will not be there, so 6kq you will get. Okay, so 6kq cos 60, 6kq cos 60 is equal to 2 6kq cos 60, and this cos 60 is 1 by 2, 2 will get cancelled, 6kq will remain. Similarly, plus this 6kq cos 30, 6kq cos 30, 2 6kq cos 30, that is equal to root 3 6kq, root 3 6kq, that is fx, plus what is still remain? 6kq, 6kq, exactly at the middle, this one. Okay, plus 6kq. Okay, 6kq, that is equal to 12kq plus root 3 6 root 3 kq, that is the x component. Okay, 12kq 6 root 3 kq. Okay, now coming to the vertical component. If you clearly observe, there is only one vertical component, that is 6kq. So the vertical component Fy is equal to 6kq. Now what is the force on Q? Is equal to Fx I cap plus Fy j cap, that is equal to 12kq 12kq plus 6 root 3 kq, 12kq plus 6 root 3 kq, sorry, kq into I cap plus 6kq, sorry, 6kq j cap. So this is the vector. If you want to find the magnitude, you can simplify it, fx square plus fy square, sorry, fy square under root. And if you want the direction, theta is equal to tan inverse of fy by fx, which gives the direction relative to the x-axis, either positive or negative depending upon the sign obtained for x component. Okay, so this is how you need to approach a problem. So it is not a complicated problem, it is just a lengthy problem. The approach is same again. Okay, So we have discussed the Coulomb's law statement and Coulomb's law expression. In addition to that, some of the properties of electrostatic force. In addition to that, some of the problem solving strategies which involves the electrostatic force. Hope the content in the video is helpful to you. If you find the video helpful, please don't forget to share, like, subscribe, and don't forget to hit the bell icon in order to get the notifications.